Today I'm going to talk about what is Lakehouse architecture and what is Iceberg, like what how it fits into the Lakehouse architecture, so why we need a new architecture for building data platforms. And so myself, Saravanan, I'm a senior data engineer working in Equal Experts. So I have 10 years experience in data engineering field, and so I have close to 10 years experience in data engineering. So let's dive into the session directly. Okay. Yeah. So let's begin with data. Okay. Hello. Hello. Yeah. So today, we'll be seeing about the evolution of data platform, like what was the earlier architecture and how it got evolved and what the industry is going towards and why we need this need. So let's start with data warehousing, right? So within any organization, there will be a lot of departments, and each department will be handling their own applications. And for those applications, they will be having a database for persisting all those data. So the challenge comes is when department, one department wants to access, or like they want to do some analysis of data on the other department's data, right? So there will be a little bit of challenge for them to access the data. So what organization they did was like, wait, let's build a common single repository. Let's bring all the data from different domains or different departments into one common repository. So that's where data warehousing emerged. So what we do is like we do ETL, like we extract, transform data and load from different source system, and we load them into data warehouses. So the technology that is behind data warehousing is similar to what it powers databases, right? So it's very similar to databases. So this is really before cloud era begins. This was everything was set up in on-prem, and we need to have a physical server, and we need to do a vertical scaling if you want to improve the scaling of the data warehouses. So so data warehouse was one of the most adopted architecture pattern for all the data platform in early stages. So what there are some limitations, right? So let's talk about some limitations and what are the pros of why data warehousing was failing. So one is data warehouses produce gives us the best in class BI performance. If you want to analyze is the past revenues or 1 year revenue or like quarterly wise revenue, it can run a query on top of it, and it can help you get the answers immediately. So it also gives us the database features like fine-grained access control, and it also serves a single truth. And one more important key point is the the ACID compliance, right? So any databases like Oracle, MySQL, right? So they have this ACID compliances. Let me give a quick example like what is an ACID compliance mean. So say you have a bank account, and there is $1,000 in that account. When you try to access that, when you do a commit transaction and you try to access withdraw $1,000, right? uh, and there is a sudden failure in the transaction, and if you go back and see your account, you should be having only the $1,000 again, so you should not be showing $0, right? So you need to do a reverse transaction, whenever there is a failure, you should do a reverse transaction. It's like all in or nothing. Similarly, in a table, right, when you try to insert, there is an empty table and you are trying to insert like 1,000 records into the table, and there is a network issue when you are trying to reserve like 500 records. So when you try and query the table, you should not be left out with impartial data. So you need to be having all in or nothing in that space. So this is one of the principles of ACID compliances. ACID just an acronym for atomicity, consistency, isolation, and durability. So atomicity is one of this feature, and similarly, like say you have a joint account and two persons are trying to access the amount at the same time, and one who is trying to access first should be given that first privilege, and second goes to the so if there is $1,000 and both trying to get $1,000, that should not happen. So each one should get like if so the first person who is accessing the data should get that $1,000, and next one should be shown as $0, or there should be some kind of an error to the invalid balance or something. So these are some kind of complaints, like acid complaints, which we get inherently from the databases. Yeah. So next, right? So there are some cons to this data lake warehouses, right? So one of the cons is like, so this is like vendor lock-in, right? So what do I mean by vendor lock-in is like, say example of an like Oracle, which is an OLTP databases, right? So we'll never know like how the data is stored underneath. So if you want to access the data, we need to use the Oracle or MySQL compute to access the data. So there is a vendor lock-in, like we can't easily switch between like databases, or like switch between different compute engine for us. So that is one of the drawbacks of the the data warehouses. And again, the data warehouse is like very structured, like we need to define the schema and tables, everything upfront, and we need to stick to that schema every time when we try to bring in data from different source system into this architecture. So these are some of the pro cons of this data lakehouse architecture. So next terms is like, so organizations suddenly started realizing like, okay, data warehousing, we are getting a lot of benefits, but nowadays we're getting a lot of unstructured data, maybe semi-structured data. So we need some place to store all this data. And if you see like a lot of ML workloads or AI workloads, they can easily work on unstructured or semi-structured. So organization wanted to make value from unstructured and semi-structured data as well. So that's where like people started using data lake. So you can see like when data started increasing, right? So we started getting data from different source systems, like we get data from medias, like social medias, and machine generated logs, IoT logs, and a lot of mainly the websites click streams, right? And these data are rarely very unstructured, and storing this data into a warehousing was a little challenging. And so data started growing, and scaling up the data warehousing was a little challenge. And that's where like data lake came into picture. At the same time, there was an rise in the Hadoop era. So Hadoop has this one feature called HDFS. You might have known that. That is called Hadoop Distributed File System. So organizations started like, okay, uh, that Hadoop file system was mainly made up of commodity hardwares, like normal storage, but it was like instead of horizontal scaling, they have vertical scaling, like parallel processing. So what like they started like, okay, we can leverage this technology to store all our unstructured data and everything, whatever we get from the different source system, we put them into the data lake. So that's where like data lake came into a picture. So so we started storing, like the organization started storing like CSV file, JSON file, XML databases, and images, audios, videos, everything into this data lake. So so normally it was again an on-premise solution using HDFS technology. And there are a lot of pros to it, like so it supported a lot of AML workloads, so people can directly access the data lake and for their data. And it is again cost effective, like since it's a commodity hardware, so it was cost effective. And one more great benefit is like it stores all type of data. So that was one of the real positive of a data lake. So but coming to the BI performance, right? So running a query, or like I want to know what is uh, the revenue for last quarter, like that type of queries running on top of this data lake was quite challenging. Data lake is similar to like a hard disk where we store all our data, but running query on top of it is because it's very challenging, because it doesn't have any of the schema or like the acid complaints which we talked about. Like there were some challenges, right? When we're trying to load some data into the data lake, and there is a transaction. I mean, when there is a network error and the pipeline fails, so we are left with impartial data. So we need to clean up that manually, or we need to come up with a solution to clean up those data. And there was some challenges with data lake as well. So again, uh, the quality of the data is not that great. So since there is no schema or something in place, there is no, the quality of the data is not out there. So again, as the cloud era began, right, people also started moving towards cloud warehousing and cloud data lake. So cloud data warehousing is not, I can give you some example of some cloud warehousing like Amazon Redshift or you know Snowflake and GCP's BigQuery. So these are some cloud data warehousing technologies. Again, they solve some of the issues which had with on-premise data, which are like scalability issues or the compute power. So, but still there will be some issues with accessing the unstructured data or structured data, which were really needed for the AML work cases. So then came the so there was also like people also who were using on-premise data lake, they started moving towards the cloud data lake solutions. So the cloud data lake mainly built on top of AWS S3, or in case if it is Azure is ADLS, or like in GCP buckets. So again, the scalability issue has been like drastically reduced in cloud part, but still there was some challenges like querying the data, was the BI performance is not that great using that. So so then some organization, what they did was they do a combined architecture, like hybrid architecture. So they extract all the data, they put that in the cloud data warehouse, cloud data lake, and from the cloud data lake, they have to copy the data again to the data warehousing layer. Like for example, they put it into a S3 bucket, and from S3 bucket, they copy again the data into the Snowflake. So before copying to the Snowflake, they transform the data, they clean the data, and very specific to the Snowflake format, like the table and everything will be created in Snowflake. So here the problem is like almost some issues has been resolved. Like now we can handle both the AI ML workloads as well as the BA workloads, but still there is some problem like we need to copy the data in both places. So same data of copy has to be copied in both data lakes as well as in data warehouses. So that is something little challenging because you need to keep up the data in sync between both data lake and data lake. And also there is some access issues as well. Like people can Snowflake gives like fine grained access control to access to their data. Like if there is any sensitive data, like it gives that. But achieving the same in data lake was little challenging. So these are some again this is the some areas like people started like moving towards like from data warehouse, then on-premise data warehouse, then data lakes, and then the cloud data warehouse and cloud data lakes, and then they also used a combined approach. So if you think of this, like we need so if you think, if you next gen, like if you are going to generate a new, we are going to build a new data platform, so we need to bring all the positives from all these existing data platform into our new platform. So for example, right, if you are going to build a new data architecture, data platform, it should be like flexible, scalable, and next is like it should be open, right? So it should not be any proprietary like vendor lock-in. It should be open, and anyone can any query engine which is compatible with it should be able to go and read the data. And some other sense is like it should be future proof as well. Like if you are going to build a data lake, it should be a future proof, and should be a user centric one, like easy to adapt. Like there should not be a high steep learning game for the team to adapt into it. Yeah, so that's where when all these positives, and we take all these positives and then we build something called Lakehouse architecture. So this Lakehouse architecture is nothing but we take all the positives from data warehouse, and we take all the positives from our data lake, and we build something called a Lakehouse architecture. So we'll deep dive into what this architecture constitutes, and where how it will be much helpful, and how it is resolving all those existing problems. So so normally what Lakehouse gives us is this, it gives the single tier storage. Like in data lake, we have that single layer architecture. Like similar to that, it gives the one single storage for both structured, unstructured, and semi-structured data. So next is like, so we have the warehouse features as well. And let's deep into the Lakehouse architecture itself, like what really it is. So this is a high level, like how a data lakehouse architecture looks like. So underneath it has a storage layer, and then you have a compute layer. Now you might be wondering, like from where does from this lakehouse, like what are the data lake features that in that got integrated. So if you have seen before, like data lakehouse, I mean data lake were being built on top of cloud storage, and on top of it we store them as CSV or JSON or whatever file format you want. So in this case, we are again using the storage layer as cloud storage. It can be AWS S3, I mean in case of Azure ADLS or GCP. You can choose any of this. And the file format we are going with is Apache Parquet, Avro, or we have three options here. Let me come back to this again. Like we have a slide dedicated, like why these three formats are really needed for it. So if you see these two things, right, this is really a data lake. Like whatever data we get from it, we store it as an S3 on top of a file format. So now we got all the features of the data lake, like the high availability, durability, and support for AML, semi-structured data. But now comes the part is like what are the features from data warehouse that got inherited into this lakehouse layer? That is called the acid complaints, mainly the acid complaints, right? So if you see, there is one layer on top of it, right? Open table format. This table format is responsible for that acid complaints. So until if we exclude this feature, right, this is the data lake, and if we include this feature, this is called the open table format, we get this data warehousing features, which is the acid compliances. So now we got that both features, like both of positives, like what have we seen in from data warehouses and data lakes into this so the next layer is the compute layer. We'll come back to this later when we start looking about compute layer. Let's little deep dive into the storage layer and what it really has. So normally, like underneath, I've said before, we have the cloud storage. Cloud storage has the offers the high availability and durability and scalability options for us. And like which is really important, right? So when we started receiving a lot of huge amount of data, this storage needs to be scalable and durable and highly available for us to access the data. Next is the open file format, and so we saw about, right, like we have three options now: Parquet, ORC, and Avro. So within this, Parquet and ORC are columnar format. Columnar format are nothing but like the difference is like how the data is stored underneath inside this Parquet or ORC file versus the Avro file. Avro is a columnar format. So now on the top we have the options. One is we have three open table formats as of currently in the industry. One is the Iceberg, one is the Hudi, and Delta. So we'll have a comparison, like what needs to be chosen at what time in the upcoming slides. So before that, we'll see about like what is Parquet, ORC, and Avro file format. So I said before, like Parquet and ORC are like columnar format, and Avro is a row-based format. So it all about like how the data is stored in the underneath. Like so, apart from that, like nowadays, Parquet is now being the go ahead, like the standard for all the data platforms, data lakes or data lake platforms. So how Parquet is different from other things, say you have a very big file, like kind of a table, and underneath table everything is stored in a file in a lakehouse. So you have like 1 million records in a table, and that 1 million records underneath is stored in a thousand files. And suppose say I want to query a ID, query a particular column, like I want to get all the data greater than Jan 1, like maybe a Jan 1 date. So if I go into like if what does the query engine does is like it goes to the table and it goes and start reading all those files. So say there are 1 million records, right? So if it is going to read all those thousand files, it's going to be it's imperfect. The performance inefficient. So in most of the time, like instead of increasing the compute power, if you think like if you can if you can, like, most of the time the compute spends most of the time in IO operation, like opening the file, going through all the file. Like if there is 1,000 files, it has to go and scan all those 1,000 files. So instead, like, what if, like, the file itself has some metadata, maybe like some kind of information, like so what it contains underneath. For example, like the file has an index or something, like saying that, okay, so this file has only date range from December to January, and this file has date range from this range. So seeing that, the query engine can prune some of the files or do some data skipping on top of it. Like, okay, out of 1,000 files, like only 10 files are going to have this files data, then I can go and only directly query the 10 files instead of like going and reading all those stuff. So these are some benefits that we get from Parquet or ORC. And like Avro is really good for writing operations. So if you see, right, like we need to collect some statistics before when we write, when we write. So if you are writing 100 million like 10 million records into the table, like we need to calculate the statistics for each file before we write it, so that only when we try to read we can do a lot of data pruning. So that's where, like, Parquet or ORC, like it will take some time for writing, but reading will be much faster. It is it is the kind of different in Avro. Like Avro provides faster write operation, but reading might be a little slow. So Avro will be good for like streaming operations, like when you have any streaming workloads, and Parquet and ORC really for good for analytical workloads. So now we talked about the storage and file format. Let's talk a little bit about the open table formats. So we have open table formats are really the brain, or something that gives the acid complaints to our data lake. So OpenGAME is something similar, like it collects a lot of metadata. So we'll deep in see this in real when we see a demo, like what are the metadata that's being collected as a part of it. So so normally it collects a lot of metadata. So this is a high level hierarchy, like all these three formats, like Hudi or Iceberg or the the Apache, like the Delta Lake, right? So nothing, don't get confused with Delta Lake with the data lake. Delta Lake is a separate open table format. Data Lake is a data architecture pattern. So so it collects a lot of metadata before writing all those files directly into the S3 or any other storage we have. So within this, like we have a lot of features we can bring in, like suppose say you have done something, we are unnecessary, like unknowingly you deleted some records. So we want to go back and roll back some, which are some features which are inherently available in databases. So we can get all those features back in our lakehouse as well. Like that feature is namely called time travel. So in case if you drop the table by accident, and it doesn't really drop the table in the backend, but it's just a metadata layer update. Like, okay, just in the meta layer, just it updates like, hey, I have dropped this table, but still the data really really exists in the backend system. So you just need to do a time travel. Look, accidentally if I delete it, we can bring back the table again. See, there some of the features, like schema evolution, and we talked about atomic transition, like which is all in or nothing. Like when you try to insert like some number of records and some failure, you should not left with impartial data. So this is the transaction layer, or the brain of the the our Lakehouse architecture. Next is the comparison, like within the transaction. This transaction layer is provided by three technologies. Like one is the Apache Iceberg, and it's Apache Hudi and Delta Lake. So Apache Iceberg is like a little bit history is like it was first developed in Netflix, and it was later open sourced, and now it is gaining a lot of traction in the data engineering community. Next one is Apache Hudi, and it was developed in Uber for real time streaming application, and it also now but it has some specific each their transaction layer has their own specific use cases. And when you're trying to implement a lakehouse architecture, it's like we need to understand what problem it really solves and other things. Next is the Delta Lake. Delta Lake was developed by Databricks, and it's mainly like if you are already having a Databricks ecosystem, it really blends into it. And again, these are the file format that is supported. So we've seen, right? So we have Iceberg, and Iceberg supports these all these formats, and it also supports all these formats. So this is a hierarchy of how the storage architecture in a Lakehouse architecture begins. Next, let's talk about a little bit of compute. So earlier we see, right, in data warehousing, like the compute and storage are tightly coupled here. Now in this architecture, if you see here, like we have decoupled the storage layer and the compute layer. So storage layer is like it will be in your AWS S3. Say it will be in AWS S3, and we have these two layers as well. And the compute is completely independent. Now we can use any other compute engine like Apache Spark, which is one predominant data engineering tool, and we can even use Snowflake, like Snowflake compute alone. Like instead of the storage, we can use the Snowflake compute to directly read all these tables and files available there. So, so any other engine, like they have the compatible with leading, they can start reading all those files directly in the storage layer. This is how, like we can independently use whatever storage. For example, Spark is good for batch loading. If you have huge amount of data and we want to do a transformation of it, Spark is a very good option for it. But in case of Flink, right, Flink is good in stream processing, so we can do a lot of stream processing on the events that are being generated in real time, and then we can also use, like, some business analysts, they prefer to use SQL as their primary language, so they can use their own query engine and to query the data from the Lakehouse architecture instead of sticking towards one technology. Now it gives a lot of options for us. So next is like now say if we used Lakehouse architecture and we built 1,000 plus tables, right? And as a business analyst, I want to know what are the tables are there in the Lakehouse. So now comes the part of data catalog. So we need a catalog to know, like catalog is the front end that exposes like what are the tables that are being created in the which are available in the Lakehouses. So it gives us the main front door to for go and access all the data into this. So it also like say we have it also acts as a metadata repository. So there are two types of like metadata if you've seen. Like one is the technical metadata. So technical is somewhere if you're creating a table, you pass in the what is the schema for this table, what are the columns that is going to be. So these are some of technical metadata, and some of things are called business metadata, like what this column stand for. They say there is a column called ID, and the business metadata means hey, this column is for denotes user ID. So uniquely identify. These are called some business metadata. So this data catalog can also be act as a single point of source, like where all the metadata can be stored, and it gives a kind of, consider this as an UI, right? So anything, if you want to go and check what are the tables, and within the table what are the columns available, so all these details will be available in the get data catalog. So, and also it gives us the ability to do the lineage tracking, and also like uh, gives us the ability to do the data governance. So we are fixing this Lakehouse bit by bit. Like we resolved what is storage, and then we resolve the compute part. Now we want to do other parts, like the governance of the table. Cannot go and access all those data. So there will be some sensitive data as well, so we need something that's the part where the data catalogs comes into picture. So it's about like data lakeouts is nothing but like we are just assembling our own data platform. That's what we can explain. So I'll give you an overview of like what are the landscape currently available in data lakehouse. So if you see the file format here, like currently we have Apache Hudi, Iceberg, Data Lake, and one interesting feature which is coming, which is in incubating, is called Apache Xtable. So Apache Xtable is not like, it helps us to like say example, there is a table in Apache Hudi, then we can convert that into iceberg table, or if there is an iceberg table, we can convert, like we can convert everything into using this Apache X table. So it is still in incubating phase, and we have these operations of available options like Parquet, ORC. These are file formats, we can say. Next, we have the catalog options. So now we have seen the file format and the storage, like how it is. Now in the catalog option, we have Unity catalog. If you have been Databricks, like you don't know what is Unity catalog. And if you are from Snowflake catalog, then we have this catalog called Polaris, which was recently open source by Snowflake, and the other catalog like Apache NAC, Hive, and everything. So if you see the outer layer, right, these are the available query engines that are currently available in market, which can access the Lakehouse architectures. So one is like when predominantly people use this as a Spark, and now Snowflake also has started, their support towards accessing Apache Iceberg tables, and we have Databricks as well. So these are the landscape, and this landscape is currently expanding rapidly. So we have talked about the this layer, like we talked very high level about like the transaction layer, like which gives the asset. Let's leave a quick overview of like how this transaction layer works with an example of Apache Iceberg. So most all those platform like has their transaction layer, right? There is a little bit of change how it is implemented, but the underlying basics is very same for all those tables. Uh, check into the Apache Iceberg internals. So just to reiterate, like where this comes into picture in our architecture is like this is where Apache Iceberg comes. This gives us the ACID compliance thing. Uh, so let's talk about this Apache Iceberg internals. Okay, so this is the Apache Iceberg internal, and this is the storage layer like we talked about. This layer can be in AWS S3, and all the file format can be Parquet or on top of this is the brain that we talked about, which gives the ACID transaction, and we have the catalog layer on top of it. So imagine that you are in a so you imagine that there is a very big library, maybe a building with 12 floors, and you want to you want to go and search for a particular book and a particular author and a particular title. So what you do is like normally we go to the librarian who's sitting in the ground floor. Okay, hey, I want this particular book, and this is a non-fiction book. I want this book. So he will tell us, like he will look into the catalog and tell, hey, go to the 12th floor. This book is available in the 12th floor. So then you go to the 12th floor. There will be, say, there is another sub librarian. So hey, now he reached to the non-fiction section. So now, hey, I want this title, and this is the author. Okay, you will go and check in that section. You will be able to see that file. So he again goes to that. So what he's essentially doing is like instead of going through all 12 floors, he's using that pre-calculated the catalog, and he is directly navigating to that path, right? So similar to that is how Apache Iceberg works. Like, so suppose say there is a query like select star and where ID is equal to 123. So how it does work is like it goes to the catalog. Hey, I'm looking for this table. Can you tell me where is this location? So catalog is responsible for giving the location of the table, like where it is staying in the S3. So it goes to the metadata file, and metadata file will have all those schema related information. So say if you are trying to access some of the column which is not available in the table, right? Metadata layer will have all the schema of the table, like what are the columns available, everything. So it will tell, hey, okay, your query looks good, and I'll give you the like another location. You go and search that. Like these type of files will be in this location. You go and search in the manifest list. Manifest list is another kind of index, right? Uh, it will also again give you another location piece, like which is the manifest file, and from manifest file we will get all the data files which are needed for our particular query. So if there is 1,000 files in the data, like you don't have to go and read all those source of files, right? This layer will help us, this metadata layer will helps us to do things. Similarly, when you are going to write something into the layer, right? So you write the data into the data layer first. So what I was saying is for reading. So when you try to write something into there, first it goes and writes everything into the S3, and then it goes to one layer up and tells that, hey, I have written these many files. You log all these files in your metadata layer. So now comes the part is like what happens, like where is that acid principle comes into place, right? So say right, you are writing 1,000 files into the data lake. So this is the data layer. You started writing all those 1,000 files, and suddenly there is a network issue, and you stop writing. So what happens is that this data layer is will have some data like of impartial data, but this data will not be logged into any metadata layer. So when we start to read, right, so it will these files are not logged in my layer, so I don't have it will not show up this in the query whatever you're doing. So this is how the Apache Iceberg. This is a very high level of how Apache Iceberg works in the back. This is not about Apache Iceberg. Like all these open table formats, the underlying principle is this. Let's quickly jump into a demo. Like so, in this architecture, what I am doing is like so I am building a data lakehouse. So this lakehouse, like if you see, we have a so I'm using MinIO for storage. MinIO is a S3 compatible storage just to run it in locally. So I have used MinIO. On top of that, I am using a Parquet file format. On top, we are using Apache Iceberg as a file open table format, which gives us the ACID principles. So for data catalog, right, we was using Lakekeeper. Lakekeeper is an open source data catalog that exposes what are the tables that are being created in this table. So for compute, right, we are using Spark and Trino or DuckDB. We can mix and match all those compute to access the data from the data lake. So if you see, I've said before, data lake, when you try to query a table, the query goes to the data lake in the catalog, the lake keeper we have. So the lake keeper will give us where is the location of the table, and it directly goes to the iceberg, and iceberg will tell us like all those. It goes through all those metadata layers, and it knows what file to fetch, and it fetches from the MinIO and as a Parquet format. It reads the file and it displays the output to the user. So we are not using any Tableau or Power BI for this demo, just for reference. Like if you have any idea like how Tableau or like BI comes into picture, this is where like comes into picture. Like Tableau or Power BI, they connects to the query engine, and query engine again connects to the catalog, and it goes way there. So, yeah. Uh, let's show you a quick demo. So I have everything up and running. So I have a one Docker file like which have all the services which running locally in our system. So as I said, like I have a one second. So if you see, like I have MinIO running in my local, and I also have the catalog, the data lake keeper in my running in my local, and I have all those query engines also running in my local. So let's go to the console. So this is how a MinIO console looks like. So I'm just logging with the default username and password. So I have a bucket created already for me. You can see here this called examples bucket. This bucket name is called examples, and it's empty now. And and also I have a laykeeper running. So this is a catalog layer. So I have a warehouse created here. Like consider this a kind of a database created for us, like demo. So this warehouse naming is very specific to data. I mean, Lakekeeper, like it can change before, like if you are going with different catalog, the name will be changed. And I have a Jupyter notebook which has all those query engines ready, up and running. So you have Trino, StarRock, Iceberg, and DuckDB ready with myself. And I have created a simple, UI to view what the contents are there inside the data. So let's start with the Spark one. So let's run it first, and then I'll tell what really happening in this. Okay. So in this still stage, right? So what I've done is like So first I said like any query engine needs to go through the catalog, right? So this is what I'm doing. Like I'm just trying to establish a connection to our catalog. So my catalog is running locally in port 8081. So I'm just establishing this catalog connection. So again for so uh, so the catalog in turn will establish a connection to Apache Iceberg. So Apache Iceberg exposes a lot of APIs. So they are REST APIs. So this catalog is a REST catalog, means like it can talk REST protocol with Iceberg. So for creating or any other for creating tables or writing tables. So this is what we are doing. We are importing some of the Spark catalog. I mean, these are some jar files that are needed for running the thing, and we are specifying the lakehouse where the catalog is running, and this warehouse is like the database where we are trying to connect. So these are some Apache Spark jars that are needed to run these files. So what we are doing is right. We are creating a catalog within Spark this is called a lake keeper. This is a catalog that is created in within Spark, so that this catalog can establish a connection to our lake keeper catalog. So this is a temporary catalog, like the kind of an object that gives you connection details to the catalog. So just run it. So now what we do is like we create a namespace. So namespace or hierarchy, like any database you saw, there will be a database, then schema, and then we have all the tables, right? So we are creating a schema inside our, the Lakekeeper database. So once done, right, you can see inside the catalog, you should be able to see a namespace. So earlier it's empty. Now we can see a namespace called my namespace. And if you see there is no tables being created, let's try to create a table inside this. So I'm creating a students table using Iceberg format. So it created a table. Let's go to the Lakekeeper and see if there is a table has been created. So I can see a table has been created. So we go and look into the table, you can see a lot of information like schema fields, what I said, like these are technical metadata that's been stored in the data lake. And we also have so now let's go to the Minio console as well, like how it get detected. So let's refresh this. This is the prefix that we included in the Lakekeeper, like how to create the table. So if you see that prefix is right. So this is the location of the table, like initial warehouse, and this is the UID that's been generated. This is generated by the Spark itself. So you can see there is a file called metadata. So now we can see one is only one metadata. So only one folder called metadata. You don't see any data files yet because we haven't inserted any data. So let's try inside this metadata, we have only one metadata just JSON. We'll come back to this later. But before that, we'll try to insert some records into that table. So let's insert some records. So now we have inserted some records. So we also do a select into to show if the records has been inserted or not. So now we can see we have inserted 10 rows into the table. Let's go to the catalog here, and maybe we'll go directly into the metadata in IO console. And you see, we now see two layers has been created. In the earlier iceberg layer, we saw that there is a metadata layer and we have physically data has been stored. So if we go and look into the data layer, we can see the Parquet file format. And this is the metadata layer that gives the ACID principle. Suppose say if any query engine wants to read this table, right, what it goes is, right, first it goes and connects to the data catalog. The data catalog will gives us the location of the metadata file. So this is the location of the metadata file first. This is our metadata file. Let's explore this file a little bit. What it really contains. And I have created a small UI to visualize these files. You can see here, right? It will tell what are the schema of this table, like what are the fields are there, and it has grade, city, all those field details, and it also has that location where the table exists correctly. So it goes to this location, and maybe let's take this example. Like This is the latest metadata which got created, and let's copy this part and try to view what. So it gives us the metadata log and all those details. And if we scroll down, there is a manifest list path. So in our iceberg architecture, there was a metadata layer, and then we have manifest list path. And this is that manifest list path. Let's see what's there in there. So it will tell us, the query engine will come to this place and it will get the metadata of the location of the manifest list. Okay, you are searching for this type of data. You have to go to this place to get the data for you. So let's copy this data again. So this is the manifest. Then after the manifest list, we'll get the manifest uh, file itself. Like on top layer, there's a metadata layer, and metadata layer will give the path to the metadata manifest list, and from manifest list, we'll be going towards the manifest file directly. So this is the manifest file, and you also see you can see that of metadata that is being captured as a part of this, like. How many files has been added as part of this operation. Like we added 10 records. So for this 10 records, one file has been added. And how many record counts, like 10 record counts that have been added. If you are doing some deletes and partitioning, all those metadata will be captured. This will be very helpful for the query engine to do all those partition, like file skipping, or like directly go to the file which needed for that a query to access the data. So let's go and check this manifest file, right? So manifest file will tell us the market location, like the physical data files, like which containing the data. So if you can see here, if you can see this data. So this also see you can see a lot of metadata being captured, like lower bounds and upper bounds. Here you can see upper bounds, right? So it will tell us like the metrics that is being captured. Like for example, like the key one, maybe the let's take this key. Key two is the second column. So the lower bound is like the name starts with Alice Johnson. So the upper bound which says like Julia Roberts. So if you're trying to say something, the name starts with M. So after J. So this Parquet file will not be given to the query engine. Instead, like which file has the data that will be given to it. So let's go and check this file, like what is really exists in this Parquet file. So this is currently this is a file which is given to the query engine for us. Okay, so we see this is the final file which was written into the Parquet file. This is the hierarchy. That's how we navigate through this. The query engine that we are trying to do is going to navigate. So we have two sections here. First, it goes to the metadata file. It goes to the metadata. It scans the metadata with metadata file, then the manifest list and the manifest file, and then it goes to the data folder, and it knows like what are the now it knows what are the Parquet files that needs to be read, and it goes and reads all those Parquet file and gets displayed to the front end folks. Now we have seen like how it really works, and so again like metadata. So now let's see, like we have created this table using Spark, right? So we can, I've said like now the storage and compute are really decoupled. So let's try with Trino to read the file. So this is a Trino configuration. So we need to install some Trino things, and let's try again. Any query engine that wants to talk, first they need to go through the catalog. So catalog is the URL we are providing it, and the warehouse name is demo, and we are establishing this connection. And this is really where the catalog gets connected to the existing catalog. So then this we are creating a connection object, and then let's say we are trying to fetch the data. Now it started fetching the data which was written using Spark using Tuno. So it's very now we can like I tried multiple things, like we can use DuckDB and we can Pi Iceberg. DuckDB is again like a query engine, like it's a OLAP analytic query engine like helps us to query the data very fast manner, mostly in local systems. And we have PyIceberg as a Python library to access iceberg tables. And we have Spark, Starrocks, and Trino. Yeah, and thing is like one more thing I just want to add is like, so I will tell like when there is a in network interruption, like we'll get a lot of impartial data that's mean. So you may be wondering like, okay, so if there is a impartial data in the file, right? So it's going to cost us, right? It's waste of money for us, right? So many open table formats like Iceberg, Outlook, they expose us a lot of maintenance job, table maintenance jobs like. So you can run this job periodically, and again that also ends up in spending some compute power. Like what it does is like it and periodically it goes and checks all those data lakes. What are some orphan files that are being there, and it tries to remove those files. And also there is some trade-off for that. Like say you deleted a particular table, and the table will just in the metadata layer only it will be marked as deleted, but physically the data files will be still there. So this helps us to do the time travel. Like if you want to roll back to the particular table version, it helps. But if you are doing that table maintenance to remove all those existing layers, you will be losing the time travel features. Like you need to have that in mind. Like how many days how many days once I need to run that table maintenance to maintain the jobs. So there, this is very high level. We still have like lot to talk about. Like optimization will not go deep into that. Like there is a separate section to how we can do a lot of optimization on top of to improve the query performance. And and that's all from my end. Like you have any questions? And